Welcome to this talk about GravitySpot. This is joint work with Andreas from the Max Planck Institute in Saarbrücken, as well as with Gino Gravanis and Daniel Buschek, both from the University of Munich. So GravitySpot is basically a concept that allows the audience of large displays to be guided to a particular location. I'll refer to that in the talk as the so-called sweet spot, by basically modifying the content on the screen. So in particular, what we do is we use different cues, such as pixelation or brightness, to subtly guide the user to a particular location in front of the display. So in this case, the cue is being applied to the answer of a quiz game, which is shown in the form of an image. So first up, the question is, why would we basically want to guide users in front of large displays anyway? So usually what happens if we have large interactive displays is that we employ different kinds of sensors. This could be cameras or eye trackers. And those sensors usually have a kind of limited tracking area. In this case, it would be desirable to make the user position in a way such that the sensor can optimally track the interaction of the user. So for example, if you think about a state-of-the-art eye tracker, this would require the head of the user to be inside a tracking box of roughly 30 by 30 centimeters at a distance of only 70 centimeters in front of the display. Another opportunity is the ability to basically guide users to less crowded areas of a display if that's deployed in a space that is very well frequented. So the user could be made to move to an area where he could interact without having to be afraid that other passers-by bump into him while he is interacting. Now, if you want to build such a system, there's obviously a couple of challenges involved here. First of all, you need, or we would basically want the sweet spot to be dynamic and be adaptable to the context of the display. For example, the number of passers-by or their position. Then second, you would want to limit the number of attention switches between the cues that we use and the content that is shown on the screen. Of course, the approach should be as robust against occlusion as possible. And then again, we would want to integrate this concept basically with the actual content so that the users do not need to take their attention off what they're currently doing with the display. And then finally, one of the requirements we had was to achieve this with only a minimal hardware setup. Okay, I'd like to provide you some brief background information on interaction with large screens, and I'll briefly talk about the audience funnel, which is a model that basically describes different phases leading to interaction by a single user with a display, and it identifies different thresholds that the user needs to get over in order to enter the next phase. So usually a user is in the first place just a passerby of a display. Now, as the display manages to attract the attention of the user, he may then basically view and react to the display. And then the next challenge is to basically communicate that the display is interactive. Now, as the user notices this, he may engage into some subtle interaction, meaning that he basically tries to find out how the interaction with the display works. And then finally, as he's being motivated, he may then engage in some direct interaction with the display. And that could be using touch, using mid-air gestures, or basically any other interaction technique that is supported by the display. This may happen multiple times as the user comes back or encounters more displays on his way. And there may be also things such as follow-up actions where the user, for example, retrieves some coupon from the display and redeems it in a nearby store. Now, what does this all have to do with GravitySpot? So the interesting thing about the concept is that it basically affects different stages of this interaction process. So first of all, the user can already be guided in the phase where he doesn't yet know that the display is interactive, or he may already be deeply engaged into interaction. Then the display guides him, I don't know, to the side, for example, as a second user arrives to also interact with the display. What is a bit more subtle here is that this approach may also impact on the phase where the display attracts the attention of the user. And I'll come back to that in just a few minutes. Now, to achieve this subtle guidance, what we do is we draw upon the concept of pre-attentive visual perception, which basically describes the phenomenon that users may perceive visual stimuli without cognitively processing them. And these stimuli can then basically be applied to the screen content. Now, when looking into previous literature from psychology, we found that there is different classes of visual cues. And these are basically changes in color, changes in the shape, or if we, for example, add motion to the content. Now, what we did in the next step is that we identified a couple of these cues, and I'd like to briefly walk you through the cues that we used for our concept. I hope that you can see that well. Here on the display, what you see is one green dot, which is basically the sweet spot, and the red dot is the position of the user. Note that they won't be there in the final concept, we just included them for your reference. So, so the first cues are the so-called color cues, for example, brightness. Then we have the saturation cue, and you can see that the saturation basically increases as the user approaches the sweet spot. We then have so-called motion cues. We use jitter, and the jitter effect becomes weaker as the user gets closer to the location. And finally, there is shape-changing cues, first of which is distortion. And then the final cue that we use is pixelation, where basically the pixels get larger the further the user gets away from the sweet spot. All right. So what we noticed early on in the project was that the different cues seem to, that there seemed to be a trade-off basically in how accurately and how fast the users would position themselves with regard to the sweet spot. And this also seemed to be closely connected to how fast the users can perceive the content. So to better understand this relationship, we basically decided to investigate different mapping functions that impact on how the cue that is applied to the content changes based on the distance of the user to the sweet spot. Now, what does this mean? So in the easiest case, what we could do is you could think of a linear function where basically the strength of the cue linearly decreases as the distance to the sweet spot decreases. At the same time, we would, there may be cases in which we want to support faster positioning, and for this purpose, we implemented a so-called quick start mapping function, where basically the strength of the cue is stronger the further the user is away from the sweet spot. On the other hand, if we want to have more accurate positioning, so for these cases, we implemented a slow start function, where the cue is basically stronger the closer the user is to the sweet spot. And then finally, we also implemented a so-called S-curve function, which tries to combine the advantages of both the quick start and the slow start approach. Okay, let's briefly look at the prototype that we used. So for investigating our concept, we basically needed a way to track the position of the user in front of the display. In our current implementation, we use Kinect, so we can use multiple Kinects. Note, however, that this is totally independent of the technology. We could also use OptiTrack or Vicon or whatever, anything that gives us a 2D position of the user in front of the display. And then what we can do is we can position the sweet spot anywhere inside this area and make the user move to that to that spot. Okay, so to investigate this and to understand how this approach basically impacts on accuracy and time, we ran a first study in the lab. What we did there is we compared the mappings I just showed to you plus two baselines. One was an arrow pointing to the sweet spot. The second one was a textual description about the direction in which users should move in order to reach the sweet spot. And we compared the 4 different mappings. The task that we gave the users was a so-called spot the difference game, where 2 seemingly identical images were shown next to each other, and the task of the users was to basically spot the 3 differences in this image. Now, as soon as the participants notified the experimenter that they found the first difference, we basically measured the time, and we also recorded the distance that the user at that point in time had to the sweet spot. Right. Okay, so let's look at the results. So what we found is that there is indeed a trade-off in speed and accuracy. So for all the shape-changing cues, which are marked in yellow here, we found that they're particularly slow, but they lead to a really high accuracy. And yeah, on the other hand, color-changing cues are kind of fast, but they are way less accurate. And what can be noted is that brightness somehow seems to be a good trade-off here. This visualization shows the difference in endpoints of users in our study, with the yellow ellipses basically being the covariance, which contains 95% of all the endpoints. And what we nicely see in the bottom row here is that the color and motion cues have a rather low accuracy and like a wide spread of endpoints, basically. Looking finally at the impact of the mapping, we found that mappings can indeed influence accuracy and speed. So for example, the time for positioning with pixelation, which you can see here, went down by 50% when we used the quick start mapping. With regard to the accuracy, what we found was that we were able to increase the accuracy, for example, for the brightness cue when you use the slow start function. Of course, this came at the expense of increased task completion time. And I'm particularly glad that we have some deployment in our work. Nice follow-up to the keynote. And the reason why we did that was that we wanted to see whether our results basically transfer from the lab to the real world. So what we did is we implemented this game that I mentioned earlier in the talk. It was a quiz game where the question was shown on top of the screen, and the answer was then provided in the form of an image to which we applied the cue. Cues were then randomly selected for each session, and we deployed this display in the entrance area of a university building. It was active for 3 months, and in total we collected data from more than 230 users, and they played more than 700 games with that. With regard to speed and accuracy, what we found was that results from the lab were mainly confirmed. I won't report the numbers here, but refer you to the paper because I want to talk about some more interesting aspects here. So what we first did is we were interested in how we can basically target users in those different phases of the interaction process that I mentioned earlier. So we had one version where we basically showed the cue immediately, and that led to that users could immediately, or basically were already guided before they noticed that the display is interactive. And the interesting thing here that we noticed was that cues that had a strong effect on the content also seemed to attract a lot of attention. On the other hand, if we first showed an explanation of the game, we rather targeted users in the later stages of the interaction process. And what was interesting here was that the cues led to a different degree of attractiveness and immersion. So, for example, pixelation led to longer interactions and the users also playing quite a lot of games. With regards to the mapping functions, we also saw some impact here. So in particular, the slow mapping functions led to like a negative influence on the game experience. So we can conclude that there is indeed an influence on engagement and motivation caused by the approach. There is certain limitations to the approach, of course. First of all, we only investigated single-user interaction. People in public space often interact in groups, so this is something that we're currently working on. What I might already say is that one of the major challenges here seems to be to establish this link between a cue shown on the screen and the actual user that it's targeted to. We only investigated playful applications, but don't see any reason why this shouldn't be applicable also to more informative applications. And then we, of course, also apply this concept to almost the entire user interface, and it would be really interesting to see what happened if we applied it only to a part of it, for example, an image that's shown next to a piece of text. There are some implications for designers. So, for example, people that are developing interactive display applications could, first of all, or would need to think about whether positioning speed or accuracy would be more important for them, and then they could basically select among any of these combinations of cue and mapping function that would fit their needs, and this visualization would show them how optimizing for one variable would impact on the other. What's interesting to notice here is that designers would also need to take into account whether the screen content should remain readable, because the cues have different impact on readability. And then they could also optimize for attracting attention, or think of whether the application should be entertaining and engaging. So this might be a goal of a public display, but there may also be cases where people want to keep interaction times short, for example, if it's like more informative and the display owner or space owner basically wants to avoid long queues in front of the display. Okay. Time to wrap up. What we showed basically was that using visual cues, it is able to subtly guide users to predefined sweet spots. And we found that both in the lab and in the field that it's possible to achieve an accuracy of roughly 30 by 30 centimeters, which should be sufficient for using it with eye tracking, which is one of our major use cases. We also showed that there is a very rich set of design opportunities, and that basically this, people implementing display applications would need to take into consideration like this speed accuracy trade-off, readability, attention, and so on. Right, and then for future work, obviously we are currently working towards multi-user interaction, and apart from that, we're quite interested in how we could integrate this approach with the actual content. So there's probably more than just applying it to just an image that's shown on the screen. Yeah, with this, I'm at the end of my talk. Thank you very much for your attention, and I'm happy to try and answer any questions. Thank you.
But when you talk to people in museums and other kinds of environments, another challenge is to get them away from your display, sort of come, interact, and then go. And so you see an opportunity for this, not just in terms of attracting people, but also getting rid of them.
Yeah, that's a really good question. So obviously, I mean, if we had a very wide display, we could use that to like make room for others, for example. But as soon as we get off the display, it gets kind of difficult because you would need to find a way to basically, apply the cue to something else in the periphery. Else.
Fade out the thing. So, I mean, just say it's been 2 minutes, now.
Right, exactly. I mean, you could just make the screen go blank, right? That would be like the easiest thing to do. I mean, with regard to the approach, I'm not sure. I mean, as I said, some of the cues seem to be more attractive than others, so we could probably try to exploit this. But in fact, I think trying to keep interaction short is it's interesting, but I'm not sure whether our approach can help with that, other than like making space for others. Maybe that would also render the interaction less attractive, for example, if they're like, you need to step to the side and create some social pressure or something like that to leave.
It's an interesting design.
Yeah, exactly. Yeah, very cool point.
Any last question? I think we're, yes?
Thank you very much for your talk. I think it's very splendid work, especially useful for Kinect environment. I'm Rosie from University of Maryland. I'm wondering how visual cues can help for future head-mounted displays, for example, for VR displays or for AR displays.
Say it again.
How such visual cues would help in VR displays or AR displays?
So is your question whether we can apply this to augmented or virtual reality?
Yeah, for example, using the pixelization, using the color difference or motion difference to indicate users to turn around and switch to a certain direction. So I think
that could work, but I mean that would be rather be credited to like in general pre-attentive visual perception rather than our approach. But I think that would be worth to try. I mean, it exploits the same basically properties of this phenomenon, right, as our work does.
Another question I have is that so only one user is supported for now. So I'm wondering how will the audience think, because the audience does not know what's happening in front of the display, and it might be weird for them to see the pixelized
exactly.
display.
So,
so that might be a problem.
Yeah, excellent question. As I said, in the deployment we just supported single users, and that of course created some kind of tension if there was more than one person in front of the display. And so the thing is, we're currently working towards solving this by making this approach applicable to multi-user interaction. And one thing that we could, for example, do was to have multiple objects on the screen and then apply this concept to those different objects. But then the challenge, as I just mentioned in the talk, is how would we make the connection between a user and a particular object on the screen obvious? So one thing I could imagine was to, for example, use the silhouette of the user, because that's very characteristic, and try to apply the cue to that. But hopefully I'll be able to talk more about this next year.
Okay, thank you very much. Thank you.